All right. We're going to be using our periodic tables quite a bit today. You're going to be using them quite a bit on the homework. What I'm going to say is this lesson is pretty short, but it's a lot. Okay. I try not to throw too much in at one time, so I made it shorter, and so that way on Thursday this week we're going to do the Oobleck lab, which is totally not related to what we're doing, but it's super fun. We get to play with a non-Newtonian fluid, which is super cool. You get to punch it, literally. You can punch it if you want to. All right. All right. Okay. We've talked about electrons. We've talked about electrons changing. Okay. Yep. All right. Ions. That should be gain or lose electrons. Now we're going to talk about where those electrons are. We're going to use, if we did our reading from last week well, okay, we're going to use the Niels Bohr planetary model, the one that looks like this. We're not going to necessarily use the quantum model because the math on that's very confusing, and also it can be overwhelming to understand how electrons truly move. But this one helps us understand energy levels, where they're at, where's the highest energy electron versus the lowest energy electron, and then we can go from there. So, as atoms gain energy, electrons can change their position. So, Hannah and I had a conversation yesterday about the noble gases. Do you remember that, Hannah?
Uh-huh.
What happens if you take a noble gas and you shoot electricity?
It glows.
It glows. So if you look at your periodic table, all the ones on the way right side, all right, are the noble gases. All right. They, all right, have electrons in such a way where if you get the electrons excited, what they do is they go from a low energy state to a high energy state with electricity going through it. But the moment it's up there, it wants to be back to its neutral state. It doesn't like being in that high energy state. So after electricity goes through it, it goes back down to this lower energy state, and then some pretty wavelengths of light go flying away. This is the sign for wavelength. Okay, it's a Greek letter called lambda, but I digress. Okay, so light goes flying away. So too much energy causes electrons to separate and start a chemical reaction or some other effect. All right. So for example, when we do some chemistry next semester, we're going to heat up some solutions, we're going to mix them together, and by them being in a high energy state, it allows that chemical reaction to happen a little bit faster. Okay. So example B, cooking an egg. All right. What happens when you cook an egg? All right. The chemicals in the atoms in the egg don't change. But what you do is you cause those electrons to break away from what they're doing and reform in a different way, which is why when you cook an egg, you break all of those protein bonds, they form in a different way, your liquid egg turns into a solid egg, and you can eat it. If you eat raw eggs, whatever, but when you cook an egg, you take those protein bonds, break them apart, and then they reform in a different way.
What about a boiled egg?
Same thing. By adding heat or energy to the system, you cause those electrons to move to a different energy state, and when they cool down, right, when your eggs cool off, right, they're no longer bound together like this, they're kind of like this. Right. And electricity through neon, kind of those noble gases we talked about. What we're going to do is we're going to learn about electron positions and what electrons do when they become ions. There are going to be some things that I talk about, but they're not necessarily going to show up on your homework. I do want you to understand them because it's chemistry, but the homework based upon it would just be rote memorization from your notes. So there's no the homework is pretty straightforward, but I digress because in order to go the next layer deeper, we would spend a really long time on it. Okay. All I want you to know is electrons, high energy states, moves further outside of the atom. Lower energy states move closer inwards. Okay. Good here? Questions, problems, concerns? Let's go full screen. Hey, there we go. Looking professional now. On your periodic table. All right. I want you to write S block, D block, P block, and you can write the F block, but we probably won't ever get there. All right. S, P, D, and F. No. All right. What I want you to know is S block is over here. P block is over to the right. D block is in the middle. And F block is down here. As far as notes go, continuing on your notes, let's look at, there is certain trends to follow. How many, right, columns wide is the S block? 2, right? So the S block specifically holds 2 electrons. All right? The S block specifically holds 2 electrons. Counting across, how much would the P orbitals hold? Super easy. Just count across. How many is that going to be? Just count across. 6. So the P block here, going across, you can hold 6 electrons. Okay. The F block I really don't talk about too much. That's just like, once you understand S, P, and D, F block is just annoying. Don't worry about it. And most of the stuff is just radioactive to begin with, so we just kind of look at it and be like, well, we're moving on. D block holds how many? 10 electrons. Okay.
And then the F block has 15, I think.
Close. 14. All right. So here's what I have in your head. The S holds 2 electrons, the P holds 6, and the D holds 10. This is a little bit of kind of looking underneath the hood of why the periodic table is arranged the way it is. All right, is because in this middle section right here, which seems a little odd that it goes up and then down, then up again, this middle section is the D block, S, and the P. All right. If we looked at a true periodic table, the F block would be shoved in right here. All right. And then the periodic table will be even longer. All right. But since we really don't deal with this too much, the common thing is to take the F block out, put it down below, and just know that the F block gets shoved right up in there. So to help follow it, if you look at your periodic table, the atomic number right here. Let's see, I'm going to look at this one. So I got it in my hand. All right. Look at atomic number 57 for me. See how it jumps to 72? Well, what's between those two? Atomic number 58 is actually the first starting the F block down here, and it continues all the way over to 71, and then 72 begins back there again. Follow me there? All right. So that's why that's kind of pulled off, is because that way our periodic table isn't this long. You know, it's this long with that part down in there. So S is 2, P is 6, D is 10. I digress. We're moving on. Here's what I want you to understand. So, pause. Never going to make you memorize this, but I want you to understand it. I legitimately had a student at the end of chemistry be upset with me because, like, you haven't taught us the most up-to-date model. There's a reason for that, okay? The quantum mechanical model, when you're looking at your S, P, D, and F orbitals, I'll shut the lights off real quick. We're going to stick with the planetary stuff. We're going to say stuff moves in spheres, and that's it. The P, D, and F actually move in these different ways. That's where the electrons are at. Super confusing. You need to know high-level math for it. But, all right, what I want you to understand is that when we're talking about this planetary model, it helps us understand it, but it's not truly what happens. Seriously, like a parent came up to me and like, why didn't you teach my parent or didn't teach my kid this? I'm like, dude, you're killing me. Okay. I'd recommend drawing this picture. I really recommend drawing that picture. All right.
Wait, so this
We already have
is
this.
gonna be-
All right. Let's draw that picture on the top right. So the Niels Bohr model, all right, which is also called the Planetary model. All right, allows us to predict where the electrons are at and where they're going, all right, and how they interact with other atoms. So when we look at chemical bonding later on, this kind of thing is going to pop up again, and we're going to see how electrons transfer between the atoms. Kingston, you all right?
He's very much dead.
Do you need to go to the nurse?
Sure.
Well, if you can make it there, so let's carry on through.
You want me to go get him on the wheelchair?
No. If you made it to class, you can make it to the nurse. All right. I'm going to unpack quite a few things here. All right. We have electron shells, we have electron orbitals, and there's one thing in here I wanted to add as well, electron suborbitals. Okay. If I count the first shell, at most it can hold 2 electrons. Do we see how the first number right here is a 1? Follow me there? That 1 signifies what shell you're in. So the first shell of electrons can hold at most 1, 2 electrons. Okay? The second shell, if we count over, can hold 1, 2, 3, 4, 5, 6, 7, 8. Because we have the 2 from the S and the 6 from the P. Okay? So the shell is the layer of electrons, and in that shell you have the orbital paths.
Mr. Williams,
Yeah.
did you know it's almost Christmas?
Aubrey, to us it's almost Christmas. To normal people, it's almost Thanksgiving or like Halloween.
Well, it's almost Christmas.
My stance on the situation is you can be excited for Christmas all you want, but Christmas does not begin until after Thanksgiving meal has been cleaned up.
Well, yeah.
There you
But you can go Christmas shopping now. It's like getting people stuff.
go. Sure.
True story.
All right, the third layer. Here's what I noticed something a little interesting about the third layer. Okay? Starts here, but it can hold 18 electrons. What? The D block actually starts on the third row right there. See how it goes 3S, and then we bump down to 3D, and then back up to 3P? Okay? So, what I don't want you to get in the habit of is trying to memorize these numbers. What we're going to do is we're going to practice a skill here in a little bit on writing the electron configuration, and then hopefully it'll make a whole lot more sense once we get there. Okay? Here's what I want you to understand. The shells are layers of electrons. Kind of think of like I was say onions, and then I was thinking Shrek quotes, and pop it in my head. Okay. The first layer is the smallest. It can hold the smallest number of electrons. The second is bigger, can hold more. Third is bigger, can hold even more. Inside of that, we can now look at our orbitals. And your orbitals are the S, P, D, and F. The things we just wrote on our periodic table. That tells us what orbital we're in. So if we were looking at the quantum model, not only can we tell where the electron is at, but not only can we tell what it's doing, we can also tell what path it's going to take. But we're not going to worry about that. We're just going to say, okay, can we know where the electron is at and how many there are? That's it. All right. And then hopefully if we do a couple of classroom examples, this will make a whole lot more sense. Mary Kate, you with us? Okay. Just make sure you come back to Earth. Get a few astronaut helmets. Because you guys are really spaced out. All right.
Knee slapper.
I think my jokes. Actually, no. I know my jokes are funny. You can think of whatever you want.
What's your favorite holiday then, if it's not Christmas?
My favorite holiday, whatever the next one I get to eat at is.
It's Thanksgiving.
Thanksgiving. There we go.
That's his favorite holiday.
After Thanksgiving, you know what becomes though? Christmas. Yeah, Hannah.
So, okay, the D block holds 10 electrons.
Yes, in total, yes.
So, would it only have 2 shells filled up? Because it would have 2 on the first shell and then 8 on the second one?
The shell tells you how many electrons in total, and that's the number out in front. So we got the 3D right here. So we have the 10 right here, plus the 2 right here, plus the 6 right here. And that's where the 18 comes from. Follow me there?
No.
Okay. So, according to this, all right, I'll go back a little bit, that way we can see this a little bit bigger. The shell is the number out in front. Okay. The third shell holds a maximum number of 18 electrons. Where does that 18 come from? We have 2 right here. 1, 2. We have 10 right here, plus the 6 right here. I just follow the 3's all the way across and count it up. And that in total gets us 18. Follow me there? Okay. Now, I don't want you getting the memorization of this, of thinking, first shell's 2, all right, don't memorize this, okay? What I want you to understand is, as the shells get bigger, you can pack more electrons in them. That's all I really want you to get from this picture. We're going to count electrons here in a second, right? And that's all I'm going to expect you to do, is electron configuration and what the electrons are doing. But what I really don't like is some chemistry teachers are like, all right, here's how you do electron configuration, and then they don't tell you why it is the way it is. It's just rote memorization, you're not really learning. Okay? So here's what I want you to understand is, the blocks tell us what paths we're taking. So S is sphere, P blocks look like little dumbbells, all right? D blocks look like really fancy stuff, look like 4 balloons tied together, or like 2 balloons with a little ring in the middle, okay? So this is what allows us to shove in more electrons, because as we get bigger, the paths change, and that way they're not hitting each other. Follow me there?
I think so.
Okay, well, I'm going to show you an example, like, okay, this makes sense. Yeah.
So the blocks, like the letters are how they move.
Yes, is the path.
And then the numbers in front of the letters are the
Okay.
what are the numbers?
The numbers in front is the shell, and that's kind of how far away you are from the nucleus.
Wait, the
So-
number of shells?
So the first shell only holds 2 electrons
I did.
because it's really close to the atom. All right. When you go to the second shell, there's more space, so you can shove in 8 in total. Follow me there? The third shell has a lot more space, and you can shove 18 in total. Follow me there? Here's what I want you to understand: is the further you get away from the nucleus, the more electrons you can shove in there.
So is there only 3 shells?
There's up to 6.
So is that what the 6 is? Or what are the numbers? I don't get what the numbers.
The numbers in front and tell you what level of the shell you're at. We will never, in this class, get to 4, 5, and 6, just because they get really confusing. We're only going to look at 1, 2, and 3.
So when you say what shell you're at, what do you mean by that?
The number in front. 2, 3, 4, 5, 6 is what shell. So first shell is 1, really small. Second shell is a little bit bigger. So this whole row right here is in the second shell. It's a little bit bigger. The third shell has all of these ones in it, and it gets even bigger. Follow me there? Okay. This is one of those things you just chew on it for a little bit and you'll be okay. Like everything we've done this year is just chew on it for a bit, you'll be okay. Yeah, Hannah.
So, does everything in the D block have to have at least 10 electrons?
We're going to be, very soon we're going to count the electrons. All right, and we're going to show what that looks like. Okay? All right. All right. I'm going to do this. We're going to talk about it. And then I'm going to show you what it looks like in your homework, okay? All right. Rather than spending a really long time unpacking Aufbau, Pauli, and Hund's rules, we're going to do them all at the same time. All right? Aufbau essentially says the lower energy orbitals get filled first. Pauli says no electrons can occupy the same space. And Hund says fill low energy and orbital by suborbitals. And we're going to do calcium as example here. So here's what I would love for you to do. Draw this, okay, with the blank squares as well. All right.
Are those S's on the left side?
Yeah, I got, right here.
Yeah.
Yep, 1s, 2s, 2p, 3s, 3p, 4s. Okay. And we're going to talk about now how do those electrons in calcium, how do they fill up the orbitals, and what does those directions look like? Hopefully your middle school teacher taught you about magnets.
No.
Yes.
Magnets, how like sides repel, opposites attract.
Yeah, remember that bag with like magnets over
If so, I spaced it.
Okay. Are you good if I put two magnets, both north side together, are going to push off,
Yeah.
and opposite sides attract? Okay.
I learned that when I was like 2. I had a little train set and they were magnetic.
Mm-hmm.
And I built tracks all over the place and they,
We're going to use that here.
I was smart with it.
All right.
I just see that little operator getting mad and like throwing stuff on the floor.
I sat there for 2 minutes
Alright.
trying to put it together.
Kinsey, can you help me out? We're going to do calcium example. So find calcium on your crack table.
Okay, I found it.
How many electrons is calcium going to have if it's neutral? 20, absolutely. So what we're going to do is, I'm going to add electrons in this diagram until I get to 20. We're going to add it in a very particular way. Okay? We're going to follow these 3 rules at the same time. The lower energy orbitals get filled first. Are we good? Are we still drawing the diagram?
I'm still right.
Okay.
She's writing all of it and drawing.
Okay.
You're supposed to write all.
You can paraphrase these in your notes.
I don't know how to. Yeah, I don't know how to paraphrase this. I don't understand it. So.
You could be extra crazy and maybe write the notes before we come to class.
We don't have no.
They're posted on Schoology. The notes are posted on Schoology before, typically on Sunday. And if I get really crazy, I do it on Saturday.
Well, yeah.
Why would we do that over?
Yeah.
To be prepared for class.
But it's not school time yet. We got lives, man.
I understand that. That's why I don't make you do it. Put your notes in your notes.
AC is, what's 89? What's actinium? While she writes it, you can explain what that is. It's my initials, so I want to know.
Make sure you can figure that out with a Google search.
Yeah, but we're sitting here doing nothing while she's writing, so I figured you could explain.
We're not doing nothing. We're being prepared for the example.
Well, what?
We're not doing nothing.
Well, yeah. Well, it is.
Yeah, I am.
Okay, this might be stupid, but how do the electrons on the outermost shell, how are they still attracted to the nucleus if they're so far out?
Magnets, opposites attract, right? You got the positive in the nucleus, positive protons on the inside, and you got electrons on the outside. They're still attracting,
Okay.
but there's other electrons in the middle, right? So it's only going to attract so far. Because if it gets too close, the electrons in the middle are going to push it away.
Yeah.
Follow me there? And so it's this little bit of balance between being too far versus too close.
So, like, what's the limit? How far could they go before they do get too close to electrons that they repel?
The ground state, the lowest energy, is going to be the closest they can be. We're talking like picometers. It's a very, very small distance. As you add energy, electrons like to get further away. If you add too much energy, you cause a chemical reaction. That electron goes flying away and it does something else.
Okay.
We'll get there, absolutely. But electrons in a neutral state kind of get bound as being pulled in by the proton, but also being pushed away by the other electrons. Which is why the first shell, the closest, has 2 electrons, and then the second shell can't get closer because the first shell's pushing it away, the second shell's coming in.
Okay.
There's a lot of math going on there, but that's a fantastic question. All right. That's not a depth to what we're going to have to do in here. We're going to do a couple examples, and you're like, okay. But you're asking great questions. All right, we good here now? All right, let's do Aufbau's principle first. His is saying that the lowest orbitals get filled first. So, how many electrons can fit in the 1s orbital? And that's 2. We already have in our notes that we have 2 electrons. But we're going to follow Pauli's exclusion principle in saying electrons are going to push each other away. So they're going to spin in opposite directions. So we say one electron's going up, the other electron's going down. We're good here? All I've done is 2. We're going to 20.
So how many are in there?
2 electrons right here. We got 2 electrons. Okay. Let's go to the second shell. We're going to fill this one up. We're going to put 1 electron going up, 1 electron going down. Because electrons, not only they're rotating about it, but they also have some spin to it. They're going to spin opposite directions.
Yeah, where did you
This
go?
is some tough stuff. Ask the questions.
Is that a 76?
It's an arrow up and an arrow down.
Both times?
What is inside that box?
I got an arrow going up and an arrow going down. Half an arrow. You can draw the full arrow if you really want to. Arrow going up, arrow going down. Now we've got 4 electrons accounted for. We're going to calcium. We're going all the way to 20. We've only got 4.
So this is that's 4 electrons in the second box?
We got 2 here and 2 here.
So it's total was 2. Okay, yeah.
Follow me there. We got 4 in total.
Yeah, okay. I thought because you made like a little line, like, when I got.
Yeah, Maddie.
How does there could be 8?
We're going to get to the 8th there. We still got the other P to fill in. We got 2S and 2P. So between all of these, we're going to have 8 electrons. Follow me there?
No.
Okay. That's the question. Yeah, absolutely. Is there 8? We got 2 here. That means I need to shove in 6 in here.
Oh, every arrow is an electron?
Absolutely. This is one of those things where it's just like we chew on it slowly as a class, and we will all collectively get there. This is probably one of the things that is probably the first super difficult lesson we'll actually do. This separates you between ICP and chemistry. Yes, Hannah.
So where is the first shell?
First shell is 1s.
And then 2s would be the second shell.
Absolutely, which can hold
8.
8. And we got 8 right there.
1.
Oh. Okay.
First shell
Follow me there?
down here.
I tell you, we got 1, 2, 3, 4, 5, 6, 7, 8.
okay.
2 all the way
single
across.
boxes on the left, that's the first shell, in addition to the 6 that can
Yeah,
fit.
and we're going to do 3 here in a second. All right? And then we're going to do 4. Notice, what's the y-axis of this graph? It's energy. So as we add in our electrons, we're also adding in energy, because electrons that are farther away have more energy, more stored energy.
Okay.
Okay? Like everything we do in this class. I'm going to go, you're going to go, ah! And you're like, okay. All right? If it makes you feel any better, your homework isn't even like this. We'll get to the next exam and be like, that's it, we need to do homework. I'm going to say yes, and you're good to go.
Does the homework have anything to do with math?
No. Well, like addition and subtraction, like the electrons we did last week.
I don't know how to do those.
Okay? And it just takes practice. Practice till we get there. All right, are we good here? We got 2 here. We've got 8 here. So I've got 10 in total. Are we done? No. What we're going to do now, we're going to add 2 in here.
Wait, does it matter what direction the arrows are pointing?
No, you can do down and then up or up and down. Doesn't matter. We just can't have both going the same direction.
Alright.
Okay? Now, technically, when you fill in electrons, they really want to be spaced out first. All right? And if you have more electrons to fill in, so we have to go to 20, we're not there yet. Okay? So now we're at 18. Last one is going to be the last 2 in 4s. We have 20 electrons. Here's what we can see. We can see each electron with its pair is spinning in opposite direction. All right? Electrons never spin in the same direction. That's what Pauli says. That's what Pauli found out. Aufbau said you fill from the bottom up. That's exactly what we did. And then Hans kind of said the same thing, is that you fill in across and up rather than trying to fill up from down. Yeah, Kens?
How would you do carbon or like nitrogen or hydrogen?
You asked some great questions. Look at that. Okay? All right, here's what I'm going to do. I'm going to draw the diagram for these. What we're also going to do is we're going to write the electron configuration. This is where your homework is based off of. Okay? You can either draw these diagrams to help figure out your homework, or you can use your periodic table in a smart way. Both will get you there. Okay? You ready? So look at hydrogen. How many electrons hydrogen got? 1. That's it. 1 electron, we're done.
Okay.
How do you write the electron configuration for this? We write 1s. So in the first shell, we're in the s orbital. And how many electrons are there? 1. That's it. That's the electron annotation for hydrogen.
Oh, because it's in the first.
It's in the first shell.
Oh, so it's only 1.
It's in the s orbital. And there's only 1 electron there.
What's the P stand for?
The type of orbital, the shape it makes. But we don't worry about that too much. Here's what I want you to have. If you look at your periodic table, s orbitals are on the way left side. They can only hold 2. P orbitals are on the way right side. They can hold a maximum of 6. D's in the middle, but we're not going to do any D examples. Yeah, Maddie?
So the B and the S are like different places on the periodic table. Is that like, then how are they the same element? Like calcium is in the, or no, yeah, calcium would be in the S block, right?
Yes, but to fill up all of those electrons, we're going to fill up all the other orbitals, and then we're going to end at the S.
How does lithium work? I think that's what she just asked, but how would that work? Because
Let's finish off Maddie's question first. Okay, did I answer your question? I forget now.
I forget my question.
Okay. How does lithium work? So that's the next example, right? So I'm going to erase this. You don't need to draw the diagrams for your homework. You're just writing the electron configuration. How many electrons does lithium have? Periodic table. What's it got for you?
3?
3. So, lithium has 3 electrons. I'm going to fill up 2 right here.
Because 2 is the max in each.
2 is the max in each. All right? But I need to go for 3. Follow me there?
So it'd be 2s.
Yeah, Hannah?
But I thought that, like, the 2s would be the first layer, and then the first shell, and then the 2p would be the second shell too.
This whole thing is the shell. Okay? We fill from the lowest shell up. Okay? So we figured out, we filled in the first shell. It's got its 2 electrons. It's nice and happy. This whole shell, the second shell right here, can hold a maximum of 8 electrons.
Because there's 2 in the first shell and then 6 in the other, right?
I'm going to tweak the word, because there's 2 in the first orbital, and there's 6 in the second, in the p orbitals.
So haven't we already filled that one?
Well, we're doing lithium now, right? We only have three electrons.
Yeah, but since we put the 2 electrons in the first orbital,
Mm-hmm.
in the second orbital, shouldn't it go for the 2p?
Oh, the p orbitals are higher energy. That's why p orbitals are higher up. You always fill it up from the bottom up. So we got 1s, 2s first. If we had more electrons, we want to fill up there. Then we would go here. All right.
But I thought that we already filled that. I'm sorry.
You're fine. This is probably hands down one of the ugliest lessons of the whole year. Absolutely, without a shadow of a doubt. Am I going to expect to say, hey, sit and get it, or we're going to be totally fine? No. I have more examples, and I have some things I'm going to pull out come tomorrow, and we're going to do more practice together as a class.
Okay.
So you don't need to have this master before you leave today. Okay. I fully expected this to be a 2-day teaching thing. Okay. And I really love great questions. What I don't want is all of you just to sit and stare at me, and in your head you're having a panic attack. All right. That's what I don't want. All right, Aubrey.
Okay, so in the 1s box, you have 2 arrows, right?
Yes.
Okay, and then you'd be on the second shell.
Yep.
Dose shell, whatever. And then that one you only have 1. So what would you write next to lithium?
Fantastic. We haven't got there yet. All right. But is everybody good? Lithium's got 3 electrons. And we're going to fill it up as 1, 2, 3. Okay. We're not going to fill any of the P because P is higher energy. We go to lower energies first. Okay. So now how do we write it? We write all the way across. In the first s orbital, how many electrons are in it? 2. In the second s orbital, there's 1 electron. So you write the electron configuration as 1s2, 2s1.
So that's how you write it.
That's how you write it.
If it had been 5, would you use the 2p box?
Yes, so what's 5? 5 is boron. So if we did boron, boron's got 5 electrons. So I'm going to do boron over here. What will we do? I got 1, 2, 3, 4.
And then would you put the 5th one in the box right there?
5.
Okay, so it would be 1s, 2,
Absolutely.
2s, 2, and then 2p1.
Fantastic.
Okay.
That's it. You can do half the homework right now. Right now you're good. Okay? I'm going to show you how to do this with the periodic table. Hold your periodic table in here. Okay. What is the other way to do this? Not drawing these diagrams out. Because these diagrams are taxing and they just take a heck of a time to do. So what I'm going to do is I'm going to do oxygen. We have 8 electrons, right? Let's count at the top. What block is on the way left side? S block. So we start at the 1s block. I'm going to erase this. That way I'm not. So we start at the 1s block. And how many electrons can fill in the s block? 2. Do I have my 8 electrons yet?
No.
That's what we're looking for oxygen, right? No. So let's go to 2s. Because if I go all the way for s, we go back down to 2. There's no p block on the first shell. We got 2s, 2. Do I have my 8 electrons? Maddie, I see the furrowed brow. Okay, I'm going to come back to you in a second, okay? All right. Furrowed brows are great because it tells me you're not doing great or you're thinking hard. All right. 2s2. Am I full? Do I got my full 8? No. Aubrey's ready to roll. Now, 2s, I go straight across. We now run into our p block. It's on the second row. It's in the p orbital. And then how many over to get to oxygen? 1, 2, 3, 4. Are my 8 electrons now accounted for?
Yeah.
All right. I guarantee you, this is one of those things. People go, and they feel bad for not getting it, and it just takes some time to chew on. All right, Amy.
So whenever you just did that, why did we use the boxes?
You can use the boxes absolutely.
You should just do it without using the box.
To use it with just the periodic table in front of you, all right, is the quickest way. And how do we do that? We got S block, we got P block and D block. an F block. We're not going to use D and F, all right, just because it gets very long. All right. What I want you to do eventually, and this is eventually, we're brand new stuff today. As you count across, all right, just write out what you have. So we're going to fluorine. Fluorine has 9 electrons. Everybody good there? Atomic number is 9. 9 electrons. You good, Dawson? Okay. We start at the first s orbital, fluorine. 1s, and how many can fit in s? 2. All right, we go all the way across. There's no p block on the first one. Now we have 2 s, and how many can fit in the s? 2. On the second row, we're going, keep going, keep going, keep going. Now we've hit the p block. How many do I have to count until I get to fluorine? 1, 2, 3, 4, and 5. 2, p, 5. Yes, Abby? Why isn't there a p block in the first shell? Helium's a punk, all right? The reason helium is on the way right side is because it's a noble gas, and it acts like all the elements over here, but it doesn't have a p block orbital. It has an s block orbital. See how there's a little hole right here? Truly, helium belongs here and over here. So in the first s orbital, all right, there's no p, which is great. I think it's a super big frustrating thing is that the second element on the periodic table has a bunch of special things about it. Like it belongs here and here, but then you also think about hydrogen, the very first element on the periodic table, is special too, because it's a non-metal, but it's on the left side with the metal. It's the more chemistry you study, the more you're gonna find that there's special examples, and everybody thinks they're just awesome, and they only get their own rules. Okay, good question. We good here on this one? There. All right. If we say so. All right, try potassium. On your own. You can use a diagram, or, all right, you can just look at your periodic table and see if you get the same answer as me. Okay. All right, bell's gonna ring soon. You only have one homework assignment this week, and I'm not tacking on much more else other than the